Hello, folks. We're shifting our perspective from the atomic level and molecular and expanding our view to encompass bulk matter, the compilation of atoms and molecules that form the materials we manipulate with our hands and work with in our labs.
Up to this point, we've looked at matter at the isolated atomic and molecular level. Now, it is important to realize that it's at that level that we understand much about the nature of the matter, but we don't manipulate matter at that molecular level, but at the level of about 10 to the 23rd molecules worth of stuff. These individual atoms and molecules must have forces that bind them together, or we wouldn't have the states of matter like solids and liquids. There are three primary types of these bulk forces we'll focus on in the next two lectures. The strongest of forces are the ionic forces between anions and cations. The second of these forces are the atomic forces, which are forces between neutral atoms. And the third and most extensive set of forces we'll discuss in the next lecture are the intermolecular forces, which are the forces between molecules, which hold molecular compounds together. It's also important that we remain cognizant of the phase of the matter we're studying, whether it be solid, liquid, or gas. This realization serves as an important context for many of the forces we want to discuss in this talk. Let's look at ionic forces. Two opposite charges are held together by a strong electrostatic force, described in physics as Coulomb's law. This force is one of the strongest forces you'll find between chemicals. Now, these forces can be observed between opposite charged atomic and polyatomic anions and cations. In the solid phase, we treat the anions and cations as charged spheres that pack closely into beautiful periodic salt structures. Remember that the anions with the added electrons overbalancing their positive nucleus will have expanded probability densities and will be best described as large negative spheres when compared to the cations, which would be smaller and dense spheres due to the increased pull of the nucleus on the outer electrons. Now, how hard is it to break these ions apart? Well, to melt the sodium chloride solid, thus loosening the bond between the ions, you would have to heat the salt at 801 degrees C or 1474 degrees Fahrenheit. The resultant liquid is known as a molten salt. Bulk ions in the gas phase are not very common at all. Just imagine how hot that would have to be. Now, as we have already stated, we would expect these kinds of salt structures also with polyatomic ionic systems as well. As an example, I've shown the beautiful sodium nitrate structure. The atom sizes were minimized so you could clearly see all the atoms. Now let's look at the second class of forces, the forces that hold bulk collections of neutral atoms and elements together. There are three major types of these forces: extended covalent bonding, metallic bonding, and weak dispersion forces. One of the strongest of these three forces is the one holding multiple neutral atoms together through extended covalent bonding. We know that covalent bonding is the sharing of electrons, and we also know that covalent bonding will come with structure rules analogous to the VSEPR theory for molecular compounds. The classic example of this covalent bonding for atomic elements is carbon. Carbon loves to form covalent bonds with itself. In carbon's case, we form many types of solids. Multiple forms of a given element are called allotropes. The three most common carbon allotropes are graphite, the lowest energy form of carbon and most prevalent form of carbon, diamond, and Buckminster fullerene, which is also lovingly called buckyballs. The structures of these allotropes give us insights into their distinctive physical properties. Graphite is useful for pencils and two-dimensional conductive layers. Notice the nanostructured layered sheets, which are called graphene sheets. It only takes a small force to move these layers across each other. The next allotrope is diamonds, which are incredibly useful for creating some bling. Because of its 3D interlocking structure, we get the properties of hardness and extreme resistance to carbon-carbon bond breaking, making this allotrope useful in the design of cutting tools. And finally, Buckminster fullerene wins for the best name for its cool soccer ball structure and for its unique abilities to conduct electricity and behave as electron sinks. These electron sinks are also called electron acceptors, which can be used to do reductive type chemistry. Buckyballs, discovered and characterized in 1985, arguably kicked off the huge growth and interest we now have in nanomaterials. The second atomic force that we want to identify is the forces seen between metal atoms called metallic bonding. Metallic bonding is the attractive forces formed between metal atoms which have relatively low ionization energies and weak electronegativities. Remember, metal atoms don't hold on to their outer valence electrons too well. If anything, they like being cations. These metal atoms release their electrons into a communal electron cloud of delocalized electrons that encompass the positively charged metal ions. There isn't a ton of directionality to this kind of bonding, so the atoms can move a bit. This bonding gives metals the characteristic properties of ductility and malleability, and with such mobile electrons, these materials can transfer electrons across the metal freely and conduct electricity extremely well. Now, it's fine to talk about atoms that have unfilled electronic shells bonding through covalent and metallic bonding. But how about the noble elements? And how about nonpolar diatomic elemental gases like Cl2 and N2? These substances are already happy, yet it is possible to liquefy these materials, though to do so we have to be at very, very low temperatures. Nitrogen gas is liquefied at 77 K, and helium is liquefied at 4 K, just 4 K above absolute zero. Now that's cold. There must be forces that we haven't talked about yet, which can hold these nonpolar, happy atomic substances together. The forces that bind these atoms are very weak, so weak that it doesn't take much temperature at all to break their bonding and for them to fly off and become gases. As we discussed in previous lectures, when we talked about resonance, electrons are not static but flow and move about within their orbitals. If they slosh just a little too much to one side of the atom for some unexplainable reason, they can create at that instantaneous moment a temporary weak dipole with a pseudo-negative charge where an atom has more electrons and a pseudo-positive charge where the electrons are absent. Then the atom has what we call an instantaneous dipole. If this happens next to a neighboring atom, the electrons in this other atom can be drawn toward the positive side of our original atom, creating an instantaneous dipole in this neighboring atom. This creation of temporary dipole is called an induced dipole. The result is that we now have a small bond between the atoms that was not there before. It is weak, it is fleeting, but it is present. This kind of bonding should be possible in all matter, but in the nonpolar atoms and elemental molecular systems, they are the principal bonding that holds this kind of matter together. These forces are what we call instantaneous forces or dispersion forces. They're also known as London forces. In the next lecture, we'll go on to explore the intermolecular forces that hold molecules together. Catch you in the next video.